Okay, this is a classical computer, and this is a quantum computer. Besides their physical appearance, what is the difference? Let's start with classical computers, since that's the one everyone is familiar with. Classical computers use bits, which can only be a 0 or a 1. If we combine these bits together, we can represent a lot more states than we previously could. This is how classical computers are able to count with just 2 states. If we want to add or subtract numbers with a computer, we can use logic gates to allow the computer to make simple calculations. Quantum computers are very similar in this way, except they use quantum bits called qubits as the basic form of information. What makes qubits very different from classical bits is that they can be both 0 and 1 at the same time. When a qubit is in both states at the same time, it is in what's called a superposition. But here's the catch. If we were to measure a qubit in superposition, it will be forced to choose to be 0 or 1 at random, which is really strange. So strange, a physicist named Erwin Schrödinger created a thought experiment around superposition, popularly known as Schrodinger's Cat. The thought experiment goes like this. Suppose we put a cat in a box and close it so nothing can see what's inside. And in the sealed box with the cat is a device that has a 50% chance of killing the cat. Without looking inside the box, is the cat alive or dead? Common sense will tell us that we can't truly know unless we open the box. Because the device has a 50% chance of killing the cat, we know that the cat has a 50-50 chance of being alive or dead. But to our surprise, quantum mechanics will tell us that the cat is both alive and dead simultaneously. When we open the box, the cat's superposition collapses and is forced to be alive or dead when we observe the cat. But before opening the box, the cat was in a blur of probability. This thought experiment sounds absolutely ridiculous, and that was his point. It was said that he was not entirely confident with his theory of wave mechanics, and is believed to have been quoted saying, "I don't like it, and I'm sorry I ever had anything to do with it." However, he was not wrong about this dual nature of tiny particles. A perfect demonstration of this phenomenon is the double slit experiment. Suppose we had an electron beam and a barrier with 2 thin slits. If we shoot the electrons one at a time through the slits, a very strange thing happens. We are left with a striped-like pattern, instead of 2 regions like you would expect. And if we close one of the slits, the stripes will disappear. What's happening? What is causing this strange striped pattern? Well, this striped pattern is known as a diffraction pattern. If we had waves pass through the 2 slits, diffraction would take place at each narrow slit, causing 2 waves to interfere with each other. This is what's causing the stripes. The strips where the electrons strike the most is caused by constructive interference, which is when the sum of 2 waves with the same phase grows to a larger amplitude, and the strips where no electrons strike are caused by destructive interference, which is when the sum of 2 waves 180 degrees apart cancel to just nothing. This means that the electrons are acting like waves because they are in a superposition of passing through both slits at the same time. If we were to measure the electrons before they get to the slits, we will get 2 regions like we expected before, and that's because we are collapsing the electron's superposition before it enters the slits. It now has to decide at random which slit to pass through instead of passing through both at the same time, which is just insane. As quantum mechanics and classical computing evolved, the idea to create a computer that exploits these strange quantum properties to solve really complex problems was born. Vectors are used to describe the state of these quantum bits. A vector is a quantity with 2 bits of information, direction and magnitude. If we have 1 qubit, we have 2 axes, 0 and 1. The direction of the vector describes what state the qubit is in, and the magnitude of the vector is the total probability of all the states combined, which limits us to the magnitude always having to equal 1, or 100%. If we wanted to find the magnitude of a vector, we can use the Pythagorean theorem to find that a squared plus b squared equals 1, where a and b is the amplitude of each qubit. Confused? Let's try a few examples. Suppose our qubit was in the classic state 0. That means the probability of the qubit being 0 is 100%. So we can express the qubit's state vector as just 0. Because the 0 state is 100%, then the 1 state has to be 0%, allowing us to drop the 1 state entirely. Here's one more example. Suppose our qubit was now in superposition, with a 50% chance of being 0 and a 50% chance of being 1. For the magnitude to be 1, both a and b have to be 1 over the square root of 2, because if we use Pythagorean's theorem, 1 over the square root of 2 squared is 1/2, which is 50%. 50% plus 50% gives us 100%. Easy, right? In my next video about quantum computing, I will begin to talk about quantum logic gates like the Hadamard gate. And in these next few videos, I will be writing my vectors like this, because it's much cleaner than the unit vector notation. So if you are interested in learning about quantum computing, please get used to the matrix notation. It will really help keep your math nice and clean. And as always, thanks for watching, and I hope you liked this video and learned something new. Peace.